from the beautiful studios of Way Happy. This is Mr. Meyer in section 11.3, independent and dependent events. Now let's talk about independent events first. Independent, the nice one. If you have two events where they don't affect each other, right? You're doing two things and they're not really related. So but you want to find the probability of both those things happening, or three of those things happening, or 10 of those things happening, then it's a really nice formula. All you do is find each probability individually and multiply it together because they don't affect each other. The ones that scare us are the dependent ones where one thing happens, it changes the outcome of another thing. So here's my first example, a six-sided number cube. It has the numbers 1, 2, 2, 3, 3, 3 on it. So it's not a regular, 1, 2, 3, 4, 5, 6. Those are the numbers on it. And it's actually colored. There's a red side and a white side, or 4 red sides, a white side, and a yellow side. And so here's two different problems individually. So first I ask you, what's the probability of tossing a 2? So you look up at this sample space right here and you say, well, there's 2 of those. So 2 out of 6, right? And then you're going to pick that die up and you're going to roll it again. And what's the chances you get another 2? Maybe I would ask you for a 3 or something. But again, you would count the probability and say, oh, 2 out of 6. And since these are independent, because you rolled the die and then didn't matter, what you got, because you're going to roll it again, and those two didn't affect each other, that's why this is called independent. And so that means you just multiply these probabilities together. Now it's probably easier to make that 1/3 times 1/3, and you get 1/9. And there's your probability of that happening. Good? So independent means that you can find the two probabilities, you just multiply them together, however many there are, and you just keep doing it. Like in part B, let's do that. It says that you toss the number cube and it's red. Well, 4 out of the 6 sides are red. Then you pick it up. So again, there's no dependency there. You haven't changed the odds on the die anymore, and you roll it again, and you roll a white. Well, there's only a 1/6 chance of that. And then a yellow, there's a 1/6 chance of that. Now, because you're doing this and this and this, you're going to multiply it together, because and in my brain always means multiply, where or means add. But I'm going to multiply these together because they are independent events. And what do I finally get there? Well, that looks like something. I guess I could reduce this to 2/3. Was that 2/36? Oh wait, that 2 is going to reduce into that, make that a 3. So what is that? 1 and 9, 16, 9 times 6, 54. 1 in 54 chance of that happening. So 1 in 54 chance that you go red, white, yellow, boom, boom, boom. All right, so that's the chance that it would happen. And those are called independent events. Let me ask you a question, and we'll be right back. Excellent work. All right, let's talk about the tougher one, dependent events. Now, dependent events are a little tricky because the fact is that after the first thing happened, all of a sudden the probabilities have changed to the second thing we're talking about. Independent, they didn't change, so we just multiplied together, we were done. Dependent, we still multiply together, but then we got to worry about what happened in the first event, in the first outcome. And there's a little formula here from the book, which is sweet and nice and works well. But to be honest, I have a hard time with it. I always got to draw a tree diagram. So let me show you how I do the tree diagram, and then we can kind of talk about maybe what the outcome is, how their equation works, and why it works. All right, so here you go. You got two number cubes. One's yellow, one's white. And we're going to talk about what happened here. So the first one says the white cube shows a 6 and the sum is greater than 9. So if the white cube shows a 6, then, I now rolled a 6. And then the next thing that's got to happen is the sum's got to be greater than 9. Well, that depends on if the 6 happened or not. If you rolled a 2, then I can't even get to 9. Where if I rolled a 6 or a 5 or something, I can still get bigger than 9. So that's why these are dependent. It depends on what the outcome was on the first one when you roll the second. Now you use that little formula, but again, I can't. So what I do is I draw a little tree diagram. I go like this. All right, you're either going to roll a 6. So the first thing says roll a 6 on the white die. So here's the white die. Boom, we roll it. You either get a 6 or you get a 1 to 5, right? You have a 1 in 6 chance of doing that. You have a 5/6 chance of doing that. So that's the chance of the first thing, or what they call probability of A up in their formula. Now the harder one, the probability of B given A. Right? So here's what I do. I know that the next thing I want to know, and I'll do that in a different color, is that the sum's greater than 9. Well, how do you roll a 6 and get a sum that is greater than 9? Well, you'd have to roll a 6/4, or you'd have to roll a 6/5, or you'd have to roll a 6, 6. And that's it. That's the only ways I can get bigger than 9. And that if I didn't get that, well, then I could have rolled a 6, 1 or a 6, 2 or a 6, 3. There's every single outcome. And as you can see, there's 6 outcomes. So 3 out of the 6 will give us a sum greater than 9. And 3 out of the 6 will give us a sum less than 9, right? Or equal to 9. And so there's my 2 probabilities. Now, what are they asking for? They're asking for you to have this outcome that you roll a 6, and then this outcome that you're bigger than 9. So you just multiply those 2 things together. But see how that second one was restricted? And it was only a 50-50 chance because you already knew the 6 happened. You already knew the white 6 happened. So there is my probabilities. What I would do is I would take 1/6 and I would multiply that by, let's call this 1/2. 1/2, and I would get a 1 in 12 chance. So there's a 1 in 12 chance that if you roll a die and you get a 6, that you'll get a 6 and a sum greater than 9. And that's how I do it. Now look at these 2 numbers. This is, by the way, this is what the book calls the probability of A. They say go ahead and figure out what the probability of rolling a 6 is. Kind of easy. And then this is the harder one. What's the probability of a sum greater than 9 given that you rolled a 6? Well, that's this part right here, right? What I did visually, the book will tell you like, hey, well, you know that you rolled a 6, so what are all the outcomes and how many of those are greater than 9? You'd be like, oh, 3 out of 6 or a half. And that's why they say just multiply those 2 together. Good. See, I told you, a little trickier. Now let's try B. The yellow cube shows an even number and the sum is 5. So again, I'm going to draw me a tree diagram first. It's either that you're going to get an even or you're going to get an odd. Well, the even, that's 50-50. So boom, we got even. So now we got that. Now we have to have a sum greater than 5. So if you rolled an even number, then when will I get a sum greater than 5? Well, that means you rolled a 2, and what would give you a sum? Oh, I'm sorry, not greater than 5. That is 5. So that means the other die had to be a 3. 2, 4 doesn't work. 2, 1 doesn't work. None of those guys work, right? So that's no good. And then you could have rolled a 4, and you would get a 4, 1. 4, 2 doesn't work. 4, 3 doesn't work. Nothing else works. And you could have rolled a 6, but that's too big. That's bigger than 5. So those are the only 2 outcomes that could happen if you rolled an even first, and then you rolled a sum of 5. Now, what if you roll an even and you don't get a sum of 5? That means what the heck did you roll? There's a lot, right? There's 2, 1, there's 2, 2, there's 2, 4, there's 2, 5, and 2, 6. And then the 4s are, 4, 1's gone, but you have 4, 2, 4, 3, 4, 4, 4, 5, and 4, 6. So what is that? 1, 2, 3, 4, 5. There's 10 ways already. And then all the 6s, 6, 1, all the way to 6, 6. So there's 16 outcomes there. And then the 2 more, 17, 18. There's 18 total outcomes right here. So after you rolled an even on the first die, there's 18 things that could happen, and there's all 18. Now, which ones do we want to know? We want to know when you rolled an even and then you rolled this. So what are those probabilities? Well, the even was a half. This was what? 2 out of, what is that? 2 out of 18. So this is 2 out of 18. So this is 16 out of 18 if you care. And so I have that one and I have this one. So what's the probability? 1/2 times 2/18, or what I would call 1/9. So there's a 1 in 9, I'm sorry, 1 in 18. I don't know why I reduced. A 1 in 18 chance that you throw a yellow cube that is even and the sum is 5. So that would happen one time when you tried this and you rolled 18 times. That's what we would expect, the theoretical probability. How's that sound? It's a little crazy, right? That is a tougher, much more challenging. Again, how would the book do it? They would say, what's the probability of rolling even? You like be a half. And then like, what's the chance of getting a sum of 5 on those half outcomes? So you have to think of all half outcomes. What's the chances of rolling a 5? And you'd be like, well, there's only 2 of them. So then you'd take those 2 and you would do 2/18, and you would be then multiplying those together and also get 1/18. So it works just as well. But I need to see them because for me, it's really tough. All right, let me ask you a question, and I will be right back for the last half. All right, nice work. So you see, it's getting a little tougher. And now I just got to warn you, you just got to be careful and you got to read nicely. So here's my example three. It's migration by region, right? So immigrants, people who come into that area, immigrants, people who leave that area. And so let's look at 3A here. They asking, what's the probability that an immigrant is from the West? So, what's the probability that somebody left the West? So, notice we're only talking about immigrants. So, these are the only people we care about. So, that's our total. So, what am I going to do? Well, I want to know the probability that they're from the West. So, there's my chance of success, or 2,654 over the total people that left the country. I'd have to add all those up. What is that? 2808 plus 2951 plus 3243 plus 2654, right? And divide that out and you will get whatever the total, what the probability was. So notice we had this chart, but we only cared about immigrants and not anyone else. All right, what about B? B says a little different. It says someone selected from the South region is an immigrant. So someone selected from the South. That means we're only talking about people in the South. And then what is the chance that they are an immigrant, that they came into the South? Well, these are the guys who came in. So that's 5,042. And it's divided by how many people were, in this, came into the South or left the South. We're talking about people from the South. So what is that? 8285. 8285. If I add, all I did was add those two numbers together, right? And so that was the total people of the South. Again, they only wanted to say someone from the South is an immigrant, and that's it. So we're only looking at the people from the South, and we're then looking at the immigrants. That was our, what do you call it, success rate. All right, what about this last one, that someone is an immigrant and is from the Midwest? So now they're saying, all right, what's the chances they're an immigrant and they're from the Midwest? That's these guys, right? That's these guys, 2951 out of what? Well, they didn't restrict us to immigrants or immigrants. They didn't restrict us from any region. So therefore, it's out of everybody. We got to add up all the numbers. And I can't remember exactly what that is. And I'm not going to type it into a calculator because I know you can do that. So I think I want to say it's around 20,000 or 23,000 or something like that. So I'm going to say approximately. But again, want to make sure that you know what numbers you're pulling. So you're going to take the 2951, you're going to divide it by the total. You got to add up all those numbers, and that's going to be the probability that someone is an immigrant and from, immigrant and from the Midwest. All right. All right, let's try example 4. Let's do a little cards. Now, I know some of you know cards and some of you don't, so this does get a little tricky, but we'll see. And then maybe let me know and I can put a chart of cards up. But if you have a deck of cards of 52 cards, and I want you to tell me, first off, it's independent or dependent, and then find the probability. So the first one is I want you to select 2 hearts. I want you to pull a heart from the deck. Then I want you to put it back. And then I want you to pull a heart from the deck again, right? So what is the probability that that happens? Well, the chance, first off, you got to decide, is that independent or dependent? That is definitely independent because you pulled a heart. Now the odds have changed, but then you put it back. So the odds are back to the original odds so that they don't affect each other. So the first chance that you pull a heart, if you don't know cards, there's 52 cards, 13 of them are hearts, right? Ace through king. So 13 of the 52 are hearts, and you're going to multiply that by, so that you put it back. And now again, you're going to pull another heart. So another 13 out of 52 chance. That reduces down to 1/4 times 1/4. There's a 1 in 16 chance that you will pull a heart and then put it back and then pull a heart again. And so this was definitely independent, and it was a chance of 1 in 16. What about selecting 2 hearts if the first card is not repeated? No, I meant replaced. If it's not replaced, right? So that means you pull a heart, you keep that heart in your hand, you pull another heart. All right, well, now that's dependent, right? Because it depends on if you pulled a heart. So go ahead and do it. The first heart that you pull, well, again, there's a 13 in 52 chance that you pull a heart. Now you're holding on to that heart. You got to reach in and pull another heart. Well, notice the number of hearts is dropped to 12 cards. There's only 12 hearts now. And the total number of cards, there's only 51 cards now because you did not put the heart back. So before, when we put it back, the odds stayed the same. But now that we held on to it, odds changed. In fact, both the hearts went down and the total number of cards went down. So we had to make sure we took care of both of those. Now, again, I'm not going to bore you with the calculator, but there it is. 13 times 12 over 52 times 51. And so you can figure out what that percentage is or what that fraction reduces down to. I guess I could have made that 1/4 to make this at least a little prettier. In fact, I will. I'll make that 1/4 times 12 51ths. And what is that? I think this goes in 3 times. So that's 3 51s. And then what is that? 1 in 17 maybe? I think so. 1 in 17. Yep. So 1 in 17 chance. So you can see the odds changed a little bit if you hold on to that heart. All right, what about this? A queen is drawn, not replaced, and then a king is drawn. So again, these would be dependent because you've changed the odds. They didn't stay the same because you didn't put the card back. So the chance that you pull a queen is there's only 4 queens in the deck. That's 4 in 52. And now the dependent part, there's no longer 52 cards in the deck. There's only 51. There is still 4 kings. So there's 4 kings out of 51 cards. And that's it. Reduce that down, make that fraction pretty, and your life is good. All right. Be good. I'll see you tomorrow and stay happy.